All right, so as we talked about yesterday, OpenDP's community effort to advance the practice of differential privacy. I'm gonna skip all the things we talked about yesterday and just hop into what we're gonna be covering today. The big three things, first off, there's gonna be a notebook where we use the OpenDP library through the context API. And then there will be a couple examples of other statistics being released with that API. And then I'll go and talk about the OpenDP programming framework. There'll be some slides. And then back to the latter half of the notebook, using the OpenDP library through the framework API, which is a lower level API that is very consistent with the programming framework. Right. So the notebook I'm going to be working off of is a first look at the OpenDP library. If you want to open up the notebook yourself, I have a link here on the side that should pop it open in the collab. All right, so I assume most of you are already familiar with differential privacy, but the main purpose of this is to consolidate concepts and I start out from the perspective of a data analyst and what they would see when they use the library. So in order to install OpenDP, just hit install it. We have made available most of the library APIs through the Prelude module to try and keep things short. And since in this notebook we're using library features that are marked contrib, these are library features that have not completed the vetting process. We'll have to opt into that explicitly. All right, so generally consider steps of a DP analysis broadly to fall into 5 steps. And these will vary depending on your specific use cases, but it's a good way to approach the problem. Generally, you start off by identifying what the unit of privacy is, then try and set your privacy loss parameters. Arguably, that might happen much later. Collect some public information. What aspects of your data are not considered private? What aspects of your data are you not going to get guarantees on? And that kind of information will help significantly with the utility of the analysis. Then we finally only now touch the data itself by loading it up into the library, and then submit DP queries to the library APIs. So there's quite a few steps here that are not even using DP. They're not even conducting DP analysis. They're just setting up the analysis beforehand. So the steps today I'm going to talk through are using a data set collected from a teacher survey. It's a tabular data set. It's consisting of survey responses from teachers in schools in a U.S. state. All right, so at any point in the process, if someone has a question, please ask. Happy to go into more detail on the question you about. All right, so we've got to determine first and foremost what exactly we're protecting. This is the unit of privacy. In the case of a teacher survey data set, the unit of privacy is the addition or removal of any one teacher's data. And since each teacher contributes at most 1 row, the unit of privacy corresponds to 1 row contribution. The way that you specify this unit of privacy in terms of the library APIs is through this code here, dp.unit of contributions is equal to 1. The unit of privacy will vary. You might find an individual can contribute up to K records. You might find that an individual can contribute an unbounded number of records, but you do know what user IDs are associated with each record. So you can still bound contributions. You might find that the unit of privacy is something more later in the process, like an individual can only influence a sum by a certain amount, and that's a sensitivity. So broadly speaking, differential privacy can be applied to any medium of data for which you can define a unit of privacy. If you're in a setting where you cannot determine how much an individual can influence the data set, then you're not in a situation where you can apply DP. Another context, the unit of privacy can be nodes or edges in the graph as well. We can make them more precise or more general than a single individual, like an entire household or a company. It's more general. More precise, something we see in industry, unit of privacy might be narrowed down to a person month, so splitting it across time or a device. And there's arguably, there's definitely drawbacks for narrowing your privacy, and that's something I'm not going to cover here, but I generally recommend to try and keep the unit of privacy to be an individual. So now setting your privacy loss parameters, I will go over this section much more quickly, but it's a similar structure. We have a library API where you can define, say, allowable privacy loss in terms of epsilon, or in terms of epsilon delta, or in terms of rho for your concentrated TP. And this here gives you a corresponding upper bound on output distances. I'll get into that in more detail later. So this is limiting how far apart neighboring input data sets can be. And this is limiting how far apart the distributions releases can be. Any questions on that so far? Good. All right, so collecting public information, classifying this as basically any information that's variant across all potential input data sets. For example, column names, or the unique values that individual columns can take on. Also information that's publicly available from other sources or from other DP releases. And so this public information will really help improve the utility of analyses. Obviously, there's not much you can do with, say, tablet data for which you don't even know the column names. It'd be difficult to work with something like that. All right, so now getting into mediating access to the data. I pulled down a data set here. This is the teacher survey data set. And then using the context API, the way that you spawn an object that will hold your data and mediate access to the data is through this API call. Spawns up a compositor. We specify what the data is going to be. We put our privacy unit and privacy loss in, and in this case, we're aesthetically allocating the privacy budget across all future queries at the start. So in this shorthand, it'll just break the privacy budget into three parts, and you can interact with this compositor 3 times and get data out of it. So in this case, since above, so the privacy loss to be epsilon is equal to 1, then each query will satisfy epsilon is equal to 1/3. All right, so then at this point, we get into the bulk of the library APIs, submitting DP queries, and this is where things will fan out. So we've spawned this context from above, which is pulling our data and tracking our usage, privacy usage. We can query it with this syntax. Each of these chained calls will transform the data and ultimately privatize it again. Assuming you're already familiar with post-processing, apply more post-processing after this, like more chain calls. Notice this breaks down into a series of data set transformations and then one mechanism for, in OpenDP parlance, measurement. They're essentially the same thing. So this does here is it determines the smallest amount of noise that you need to add to make the entire query satisfy epsilon is equal to 1/3 when the privacy unit is one contribution. There's this missing parameter here. You would typically expect a scale parameter there to determine how much noise you're going to add, and that's filled in based on the context, based on the known privacy budget allocated for the query and maybe the privacy. So what this does here is now that I've created this query, I haven't released it yet, but I can look at what the scale parameter is going to be. And there's a library API to determine what the accuracy of this query will be, given the scale parameter we have. So we say when the discrete Laplace distribution scale is 3, it was oh no, I don't want to debug things right now. It ran just a few minutes ago.
Oh, okay.
I think I might have a local thing that's. Yeah, okay, so what was happening there was I had development environment thing set up and it was conflicting with. So if I just do a clean install of the library, then we wouldn't have that issue. Actually, things that interfere. Sorry about that. So anyways, the parameter scale, or the parameter that was discovered for the scale is 3. And I plug this in to this helper function. It tells me with the 95% confidence, we expect that the noisy answer released by the query will differ from the true answer by at most 9.44 when the scale parameter is 3. So surprisingly often, these accuracy estimates come in use. And now finally, we have this query. We're happy with the accuracy of it. We can release it. And this is what's going to spend the budget and consume one of our 3 queries. You can obviously build a confidence interval from the accuracy estimate we had before and the DP counties. So a bit of a longer query. This is could be the mean.
And so for this, this
Yeah.
one, it actually, the DP result was actually the real result.
Oh, yeah, yeah, so what we're releasing here is a GP count with sensitivity 1. And allocating epsilon of 1/3 to that is a bit overkill. So the amount of noise added happened to sample 0 in this case because the density has the density is very high. Calibrated distribution. Okay, so this is much more with the query. I'll look at the steps more closely this time. First step here is parsing the CSV, selecting a column out from the CSV. It's casting one of the columns to float. It's doing a clamp. Resize. A resize is another kind of transformation that makes it so that the size of the data set is known to the privacy calculus. And then a mean transformation, and then applying what loss noise. This is pretty lengthy. We have put a lot of work into developing APIs that are shorter than this, and I'm excited to demo them for a 0.10, which is coming up hopefully sometime this week, maybe next week. But yeah, at the time, there's lots of very explicit steps. These will go away. That's hopefully in the near future. But the general gist will remain the same. Responding queries, you're transforming the data, you're applying a measurement, maybe some post-processing, and releasing it. So we support a lot of statistics in the library, hopefully more throughout the summer. Variance, histograms, quantiles, PCA, hopefully a new way to compute PCA this summer. Sparse histograms, more, as well as the combinations with other mechanisms like the Gaussian mechanism and other privacy accounting tools like zero concentrated DP. Great. At this point, any questions? If not, I'll switch over to more exercises, just showing more demos of how these APIs are used. Right, so this is going to use another data set, pedestrian traffic data. So for the pedestrian traffic data, it's sightings of an individual on 3 streets, Park Street, Bridge Street, and Market Street, Sydney, from February 3rd. The data is based on true counts of hourly per street pedestrian traffic, but there's some additional synthetic attributes like the name, age, and gender. So Sydney isn't actually publishing names of individuals and ages and genders that cross certain streets at on certain days, which is great. But I've added those in afterwards to make a more interesting data set. This is just pulling it down. So in this data set, we have the first sighting of individuals on each of 3 streets, which means that since the data only spans 1 day, and only the first sighting of an individual is logged, we consider there's only 3 streets or 3 contributions that an individual makes to the data set. Let's double check it, please. What is the rationale of having split data frame as part of the query and not as part of the context? It could be either way. Actually, if you have one way you can do this is you could start a compositor that just has an unparsed CSV, and you can spawn a second subcompositor that has the parsed CSV inside of it. And it just takes one query that spawns a new compositor. Maybe a bit more technical answer than we hoped for, but you can push. You can consider the parsing of the CSV as in and of itself privacy sensitive computation. It could be unstable. It could parse incorrectly and result in a greater influence a person on the data set than you would expect, result in underestimated privacy parameters. So it's like part of the computation, but you could make it not part of the query. You could make it part of the parent component. All right, so a privacy unit in this case is 3 contributions. Let's allocate epsilon of 1 for the entire analysis. We're going to consider these things public information, column names, and the unique street names that an individual can be reported on. The actual form of the data, you have a column for the street name, you have a column for hour, you have a column for the first name, last name, age, and for gender. So as before, we spawn a compositor. It's context that we can query. Plug in our privacy unit, privacy loss, and split evenly over 10 queries. So in this API, we're splitting data frame again. We're constructing a new column that checks if the street value is equal to Bridge Street. We're doing a subset down, only including individuals who or data that corresponds to Bridge Street. Selecting a column out in the count and adding the plus noise. So this ultimately gives us a count of the number of individuals that were cited on Bridge Street.
Column necessary. Like that calculating count was.
Right, so broadly speaking, you should be able to do a count directly on a data frame. But that's not directly supported in the library APIs. Take just like another constructor. Instead of adding that, we've gone down the route of doing it better in pullers. So this does a similar thing. It counts the number of sightings on all 3 streets simultaneously via parallel composition. Instead of doing a subset down, it's just counting. Is resulting in a vector of counts that will itself be noised. So the first value corresponds to Park Street, Bridge Street, and Market Street. Park Street, Bridge Street, Market Street. There's another example of releasing a distribution of pedestrians per hour. So this is going to involve a similar query. We're going to count categories. We know that categories for the hour column are the numbers 0 through 23. Similarly, release distribution of counts here over time. So the main thing I'm trying to do here is give a sense of how the context API works. We're building up a library of lots and lots of smaller primitives, and through the chaining of these primitives, we can build up more complicated queries. And each of these primitives have isolated, well-contained privacy or stability properties. Shlomi, yes. It does. Let's do another example for analyzing ages. We're going to submit queries for the mean and variance of ages on Park Street. So this builds a query. It's just a transformation at this point. We use that to construct another, to complete the query, pass the mean, release that, and we can use the same base query here to construct a variance estimator, release that as well. Each time you're releasing these, it's assuming the budget. We've got 10 to start with. It's much less now done so far. Quartiles and quantiles in general are also supported in a really atomic level view. It's using a transformation that builds a vector of scores, one score for each potential candidate quantile, and then choosing the quantile with the best score noisily using a report noisy max mechanism. Another example of a mechanism in the library is releasing sparse histogram. What this is doing here is subsetting down to Park Street and then selecting a column. We're selecting all first names. We want to release a histogram of the occurrences of first names in the data. So this will this one creates essentially a dictionary where the keys are names and the values are counts. And then this mechanism will create a compressed representation of the space of counts and noise that compressed representation, and then release something that you can interact with, just like a compositor, to ask for counts for specific individual names. My name happens to be really common, so I put it first. It's the highest number of observances. We're trying to get demos. James is less frequent at 0. Sharon is even less frequent at 0, or usually when I run this. It's randomized, of course, so I have to get some luck to get the demo just right. But Lancelot is not observed in the data, so this guy ends up being 0 with high probability. All right, so there's a flavor of OpenDP library APIs in its current state. If there's any questions about this, then please shoot.
I had a question about the meeting on like the lesson before. Well, like, I saw that there were two approaches, like resizing and then getting the count into some separately. But you put like the DP count inside of resizing. Like, could you explain it to the differences?
I don't think there's a DB count inside of the resize. There wouldn't be much point in doing a DB count inside of a resize. It'd be like a zero sensitive query. But there are definitely multiple approaches of estimated means. A lot of, like one that you're probably familiar with is estimate the count, estimate the sum, and then post-process. Another way of going about it is having a two-stable data set transformation that resizes. And with that, you might, let's say you have a prior on a general sense of what the data set size is. You might say, if there are fewer records than that, then impute additional records to make it have that many records in the data. And if there's more records than that, then sample down with a simple sample. And so that gives you the knowledge of data set size, which makes the sensitivity of the mean finite. So they have trade-offs. One can be better than the other, depending on how strong your prior is and how much information you have in the data set. Use whatever you think is best. There's another paper that I have in submission that gives a better, an even better estimator for them than estimating the count in the sum. So if you ever want to talk about that, it's fun. Interesting. It's an approach. Okay, so without any questions on that, I'm going to move on towards the programming framework. I was trying to do that kind of quickly. I feel like most people have a decent sense of DP, but some useful context to bring out of that is the privacy unit and the privacy loss being concepts that you should keep in mind as we go forward. All right, so the OpenDP programming framework is the general tool we use to represent all privacy-aware computations in the library. The framework has a generality and privacy definitions and algorithms. So it's possible to represent algorithms that satisfy pure DP, approx DP, concentrated DP, FDP, and so on and so forth. Hopefully adding RDP in the summer. We'll see how things go. There's some other definitions that we have in the works. Similarly, the generality of the framework allows for example, node level privacy in graphs, user level privacy in streams, user level privacy without streams, and so on. And the generality in the privacy calculus allows for combinators, things that build up more complex differentially private algorithms from smaller pieces like composition, amplification by subsampling. Group privacy is not quite a fit, but it's well represented in the framework. So we also have the ability to create safe extensions of the framework with better contributions. Because we have a clear specification for each component's privacy relevant properties. So I'll talk more about transformations and measurements in slides. Those are the two pieces that encompass all of the privacy stability relevant computations. And interactive differentially private algorithms are first-class citizens. They can represent all interactive DP algorithms via variables. So that's like an adaptive composition or sparse vector. So we're building a modular, flexible library via measurements, transformations, and combinators. Measurements and transformations are the building blocks, and you can glue them together via combinators. Chaining is one that we use quite in the demos from before. We used chaining composition constantly, even though it wasn't necessarily obvious. And the nice benefit of this kind of structure is that privacy proof is automatically derived for complex DP algorithms, assuming that they're built up out of these smaller and easily provable primitives.
Got the proofs that are PDFs, and that's not what you mean.
Right, so the proofs for the PDF proofs are proving individual measurements, individual transformations and compositors, combinators. But when you stitch things together, we don't need PDFs for those as well. We don't need to write proofs for those as well.
It's just like, we know that this was true and this was true, so it's not like we have an artifact that is the privacy proof that's been
Right,
derived, that
right.
we have confidence about.
If, so back here in the notebook, I don't need to write a PDF. We take proof
Okay,
for this guy because it should follow from each of
we have
the
confidence of that.
constituent proofs. Yeah.
Okay.
So first off is measurements, and now we're getting into the math finally. Say a randomized algorithm that maps from some dataset domain X into some other set Y. Satisfies epsilon delta dp if for all neighboring datasets X and X prime in our data domain, we have this inequality. So doesn't matter what the set of outputs is, the probability of observing an output in that set doesn't change much. It changes by at most a multiplicative factor of e to the epsilon and an additive factor of delta. So measurements encapsulate this privacy guarantee and more general guarantees as well. They guarantee that close data sets map to close distributions. Starting out with close data sets, we know that in this definition, we specified that their data sets are neighboring. That's what makes them close. And may result in close distributions because of this inequality. So a measurement is valid if it satisfies this privacy definition. And they allow generalization to other arbitrary measures of closeness. Closeness in terms of the inputs or closeness in terms of the outputs. We also have transformations. Transformations are very similar in concept, but they have some important distinctions. They in a general sense, map close data sets to close data sets. Sort of measurements that map close data sets to close distributions. And given that a transformed data set is also close, it's also neighboring, it makes it possible to ultimately chain with a measurement that requires close inputs. So starting here with adjacent data sets, close data sets, applying a transformation as we did here. it results in another adjacent or close data set. And continuing to apply transformations, we result in close data sets that can be then privatized via a measurement. Any questions on this?
I'll have maybe, do you have an example of another notion of closeness other than one row differs?
Yeah, so there's even two different notions of closeness where just one row differs, and potentially more. You could say there's a notion of closeness for when the order of the data set elements matters, or when it doesn't matter. Moving out of the box of adding or removing a row, you could say changing a row is another definition of closeness. Another definition of closeness could be adding or removing a node in a graph, or changing a node in the graph. Another example would be, let's say you have a data set where you don't know how many records an individual may contribute, but you do have a column that identifies which records came from which individuals. So you might have a notion of closeness that measures distances between data sets by counting the number of added or removed or changed user IDs. And then another simpler one, but in a different sense, is there's different notions of neighboring data sets in terms of sensitivity. So you might say that if you have two scalars computed via count, you haven't added noise yet, and you know that the sensitivity is 1, then these two scalars are adjacent data sets that differ in terms of their absolute distance by at most 1. Or similarly with, say, LP distances, if you have vector body queries. Or if you're in local DP, sorry, I'm going through way too many of these, but if you're in local DP, you might say a notion of distances for neighboring data sets is the discrete metric. Whether one thing is exactly the same or if it's different. So there's lots of notions out there, and it's very much a plug and play kind of thing. Each transformation has like one fixed notion of neighboring on the input, and it might have a different notion of neighboring on the output.
Great, thanks.
Yep. And there's a similar concept for measurements. So we have multiple ways of measuring adjacency for data sets. We also have multiple ways of measuring privacy for distributions. UDP, FOXDP, CCDP, etc. All right, so what are transformations and measurements built out of? Transformations have 6 pieces. They have an input domain, which describes the set of possible inputs to the function, to the transformation. They have an input metric, which is what we were just talking about. How do you measure distances between adjacent data sets? They have an output domain that is describing the set of all possible outputs that can be reached from all possible inputs to the function. There's an output metric, which could definitely be different from the input metric. There's a function that actually touches the data and does things to it. And then we have a stability map. Similarly for measurements, we have an input domain describing the set of all possible inputs to the mechanism or to the measurement. an input metric, a output measure or privacy measure. Essentially the same concept. A function that adds noise or does whatever the mechanism would be expected to do, and a privacy map. So these two pieces, stability map and privacy map, are bolded because they're probably a new concept. Might be best to give an example for, say, a transformation that is some transformation. So for the sum transformation, your input domain would be set of all vectors of, let's say, integers. Your input metric would be the symmetric distance, which is counting additions or removals of records. Your output domain would be the set of all integers. And your output metric would be the absolute distance. Obviously, the function would just compute the sum. And the stability map captures the stability properties of the function. So if you can add or remove any one record from the data set, then the stability map would be a function that takes in a data set distance in terms of the input metric and outputs a data set distance in terms of the output metric. So for the sum would be the number of records an individual can contribute multiplied by the max of the absolute value of the lower bound or the upper bound. So what this stability map tells you is, let's say I know that an individual can contribute one record. If I were to pass one into the map, then it would tell me what the sensitivity is on the resulting output data set. Similar concept here for the privacy map. If I know that input data sets may differ by at most, let's call it dn, an input distance, in terms of the input metric, then if I pass that into the privacy map, it'll tell me how far apart the resulting distributions can be in terms of, say, epsilon, or in terms of rho or epsilon delta. Any questions on this so far? This is kind of a heavy slide, so.
It would help to have another like stability map example. Okay, you can type one out.
Yeah.
That's okay.
Kind of good example. Sorry, I'm bouncing around so much.
Even if it's like pseudocode or something, just
All right, now I have an example. So this code here uses that lower level API to build a transformation that does a sum. It's pretty explicit about those 6 pieces. We specify the input domain here. It's the space of all vectors of floats bounded between 0 and 5. And then the input metric is the symmetric distance. And you pass it into this function in the library, and it gives you a transformation that have all the other 4 parts filled in. Specified what the input domain is, what the input metric is, and the library has given you a transformation that also has the output domain, the output metric, the function, and the map worked out for you. So if I make a really small mock data set, and I pass it into the function, into the transformation, what this does is it invokes the function inside that transformation, and it gives you 10, which is the sum. I can also invoke the stability map on the transformation. Let's say I know that an individual may contribute up to 2 rows. Then if I were to invoke the stability map, then it tells me that the sensitivity of the output is 10. So it's mapping from an upper bound on the distance between adjacent input data sets to an upper bound on how far apart distance between adjacent output data sets. We know that the input data sets may differ by at most 2. After summing, we know that the output data sets may differ by at least 10. That's because in this case, so this was the same map I described verbally. We have a DN of 2. We know the bounds are 0 and 5. When it's computed, it should give you 10. It's slightly larger because we're counting for potential floating point inaccuracy. Does this example help? Okay. Another example would be the clamp. The stability map on the clamp is pretty simple. It's a one stable function, so data sets that are apart by at most 1 addition or removal of an input. After clamping, they're also apart by at most 1 record on the output. So the map in that case just is the identity function that passes the distance through. The APIs are similar here. We specifying input domain, input metric, pass them into the library constructor function, as well as some auxiliary arguments like bounds to clamp to. It gives you a transformation where the input domain is unbounded, the output domain is bounded. The input metric is the symmetric distance. The output metric is also the symmetric distance, so it doesn't change the metric. The function obviously just clamps the data, and the map is the identity function as we talked about. So the library is basically built out of 100+ functions that build up computations from these little pieces. All right, so these 2 concepts are very similar. They have a lot of the same pieces, but there's a couple pieces that are different. We don't have an output domain. The output of a measurement is beyond the privacy boundary. We don't need to track that information anymore.
So what we saw are stability maps,
Yeah, that was the stability map.
and those are essentially useful for, I guess, utility
It's,
analysis and when you try to chain transformations, I guess.
yeah. Mainly for chaining transformations together.
Okay.
That way that the measurements can be, can have one concern, like all they do is add noise, or all they do is just the meat of it.
And then the privacy map,
Yeah,
what's that?
I think I'll go back to the same. notebook. So I showed the sun, the clamp. Starts off with a loss mechanism. Here you define the the input domain, the input metric as usual, as well as auxiliary arguments. It gives you a measurement. The privacy map on this measurement takes in this case, a sensitivity, and it outputs an epsilon. So when you know that the sensitivity of a scalar is bounded and you add some false noise to it, then you can compute what the privacy loss is. The map in this case looks like this here. Passed in a sensitivity to the function, it divides it by the scale, and it outputs epsilon.
Okay. And if you would be to have like the Gaussian mechanism
Mhm.
and approximate dp, it would give you a function or?
Yeah, so there's many ways you can implement it. The way that we've gone is the Gaussian mechanism only emits rows for ZCDP. And there's a separate combinator that translates the row into an epsilon delta curve. But yeah, you could definitely just say, theoretically, you could say the output measure, privacy measure for the Gaussian mechanism is epsilon delta. And what you get out is not a scalar, that's like a row or epsilon. What you get out is a function. And the function takes in a delta outputs an epsilon. So then you get a whole curve.
Okay.
Yeah, so on the current library design, it always outputs row for ZCDP, and if you want things in terms of a proxDP, then you convert it, or you can leave it in ZCDP and do composition of the rows. And for RenyDP, since conversion from ZCDP to RDP is tight, then you can have a conversion from ZCDP to RDP without needing to complicate the Gaussian mechanism. So that's stability maps and privacy maps. Hop back to the slides. We've dropped the output domain because we no longer need to track that information. It's a DP release where we can use post-processing after this point. We've changed the output metric to be an output measure. And we've renamed what this is called. It's still just a function from a D in to a D out. But the semantics are different. So then when we do chaining, let's say we have a transformation and we have another transformation. So we're looking at just this part of this so far. When we chain these together, we end up getting a new transformation that has a function that's just the functional composition. If you were to call the function on the chained transformation, it would first call function here. And then function here on the output of that. Similar idea for the maps. The maps compose functionally. Pass a dn to the map on T1. It gives you an intermediate distance for these adjacent data sets. Pass that into the map for T2, and it gives you an upper bound on distances between output data sets. The same logic holds when we then change with the measurement. Let's say we have one chain transformation here, and we change with the measurement. The functions compose and the privacy maps. Stability map from the left transformation composes with the privacy map on the right measurement. Out of this, we can build up arbitrary computations that so long as the metrics and the domains match each other, you can chain them together. Another opportunity for questions.
The notion of adjacency is defined for computation, like you use at the start of the notebook, you define that, or you, I guess it doesn't make sense to mix them across.
So remember, we defined a privacy unit.
Yeah.
A privacy unit is essentially two things. It's a input metric, and it's an input distance in terms of that metric. So yeah, you define these things up front when you define your privacy unit and your privacy loss. You fix the input metric to the very beginning, input distance, and you fix the output metric, output distance, and everything else should be.
But for example, if I want to make two separate releases.
Yep.
Can I use different privacy units in terms of this neighboring relationship?
Yeah, so you could construct. So yes and no. Like you could.
It's just like curiosity.
Yeah, right. So you can make a measurement that has an output measure in terms of QRDP. You can make another measurement that has an output measure in terms of ZCDP. And if you apply both of those to your data, then your overall privacy loss is the privacy advantage in both. In practice, you want to fuse them all under one repository, most likely. So you take the these measurements and you apply combinators that convert their privacy units into a common privacy unit. And then you can pass each of those measurements into a compositor. The compositor can have a place all these privacy units. And so that's complicated. We don't want users to have to deal with all that. So if you use the context API, it like does some level of automatic conversion depending on the privacy units you set and the mechanism you use.
Okay. I can just hear about this after the presentation.
No, I like the questions. It's like if you have a question, then most likely I'll give you a question as well. All right, so I'm spending lots of time on a lot of time on maps because they're pretty central and they're probably the new concept here. I've mentioned a couple times D-outs and D-ins. D-in being an upper bound on the distance between input data sets, and D-out being an upper bound on the distance between output data sets. Say D-out is equal to map D-in means if two inputs are D-in close, then their corresponding outputs or distributions are D-out close. So this is kind of changing the topic a little bit. Interactive measurements. The way that we represent interactivity in the library is through variables. Sorry about some new lines on these. Variables allow for some statefulness inside of them. And anytime your adversary or analyst submits a query, Q1 to the variable, it updates its internal state, returns an answer. Variables are a very general concept. You can say maybe you have a variable that represents a compositor. Your state in the compositor is your data set and your privacy consumption. Number of queries you have left. When you submit a query, the query is itself a measurement. And the internal like state of the variable will be adjusted to have the privacy loss that's advertised by the measurement now recorded inside of it, and then it returns the output of the measurement. So variables are like general state machines. You can use them also to represent, say, sparse vector or advanced kind of composition odometers, control series as well. I think I can skip concurrent composition. This is
Just on the last slide, like, don't think variables have something that's in the framework section of the docs right now. We're sort of saying these are the first class things. Should there be a variable thing in there? If we're saying it's a first class thing in the framework, or is it like not as first class as the other first class things?
It's a good question. I feel like it runs the risk of being too internal.
Okay.
Like I feel like most of the time people care about compositors, they care about mechanisms that are interactive, like switch vector.
This is how we get the thing.
It's how we get there. Yeah.
Okay. I think it is something I've wondered about, like how to, because you use it, but where does it get explained and get to work on?
Might be good with developer docs. All right, and then the various forms of compositors we have in the library allow you to spawn multiple compositors at the same time and talk to them. You can interleave your queries amongst them. Have a new August 23 last year. New feature. All right, so I started this talk with this notebook, a first look at the OpenDP library. We talked about the steps of a DP analysis. I got down to the part where it dives into the framework API and I popped out. So I'll finish that last little bit and that'll be the end for today. So okay, framework API. We have two APIs. You could say we have potentially more, but these are the two I'm going to focus on. The context API, which is this one we were showing here, dot query, you chain a bunch of dot calls. The framework API follows very closely to the OpenDP programming framework. So you directly manipulate transformations and measurements and have access to the maps. So you can determine what intermediate sensitivities are or stabilities of functions are. before, when I assigned privacy unit is equal to dp dot loss of, or I'm sorry, dp dot unit of, what it really was building was just these two items, input metric and dn. In this case, dn is 1, saying that number of changed records can be at most 1. Number of contributions can be at most 1. My privacy loss is exactly the same. It breaks out into two items, the privacy measure and the T out. Instead of calling dp.context.depositor, you can directly call the constructor function. Essentially, everything in the library is written in terms of constructor functions. These functions that take in the domain, the metric, and some auxiliary arguments. They build measurement for you, or the transformation for you, with the vetted guarantees. In this case, you specify the domain, the metric, the measure, how far apart data sets can be on the input, and what your privacy allowance is for each query. It gives you a measurement. When you invoke the measurement, it gives you a queryable. And now this is the thing that's tracking the privacy loss for your data. At this point, you could essentially just tell data, delete it. You should no longer touch it. All the privacy all the privacy calculus should ideally be handled by a variable. This snippet of code builds a transformation. This right shift syntax is the equivalent of the dot syntax in the context API. Pulling down constructors from this transformations module. I have a transformation that computes the count. If I were to run the stability map on that, then the sensitivity ends up being 1. This low-level API, you need to use a binary search utility function to calibrate the scale parameter. That's going to do here. Starting out with a transformation that computes the count, you then chain with a measurement that adds in false noise. The entire thing should satisfy D out over 3 dp. So it'll look around for different scale parameters until one satisfies this tightly.
Context is, this is like something that context is.
Yeah, context penalty for you.
When would you use this API versus context API?
Use the R.
Yeah, if you're using R.
Yeah.
And let's say if you are interested in directly accessing stability map. If you want to look at the domains and metrics being used along the way. So those are the major things. And we built this API first, so it's more useful from a developer's perspective. If you're trying to write contributions for the library, then you're going to be writing constructor functions. You're not going to be writing context APIs. Context APIs will just kind of magically appear automatically. So it's more developer oriented.
Yeah.
Okay, then what happens here? We have a measurement. We pass it into the variable. The internal state of the variable is adjusted. We count for this new privacy loss, and you get a release out. Similarly, we construct a measurement for the mean. Pass it into the variable. We get a DP estimate of the mean. All right, so that was a lot. think it's the last chance for questions in this session, but I'm always open to chatting more offline. Slack.
Yeah, thanks a lot, Mike. That was great. I'm sure we'll have some questions
Yeah.
after lunch. Does anyone have any questions or input? No, okay.
All right, I think that wraps it. Tomorrow is gonna be more of a focus on library internals. So how do you actually build measurements and transformations? And Thursday we'll cover more about groups. Thanks for your time.
Thanks, everyone.